10.1 is about sequences. A sequence is a set of numbers that follow a pattern. Each item or number in a sequence is called a term. One kind of sequence that we're going to learn about is called an arithmetic sequence. So in an arithmetic sequence, the way you find the next number in the list is by adding some value, and then you just keep adding that same value to get the next number. And that value is called the common difference. The other kind of sequence we're going to learn is called a geometric sequence. The way you find the next number in the list, if it's a geometric sequence, is you multiply by some constant. So you just keep multiplying by that value to get the next number in the list. That item that you're multiplying by, that value that you're multiplying by, that's called the common ratio. All right, in these first three examples, we have arithmetic sequences. So the way you find the common difference, which is called D, you could just take the second number and subtract the first number. So the common difference here is 4. And so now we have to find the next 4 terms. So if it goes from 7 to 11 to 15, let's just keep adding 4. 19, 23, 27, 31. All right, and now we need to graph those. All right, so the way you graph these, if the first number is 7, you're going to graph the point 1, 7. And then the second number is 11, so we're going to graph the point 2, 11, followed by 315. And then 4, 19, 5, 23. And it doesn't look like the rest of them are going to fit. I think you guys get the point. All right, for number 2, notice the values are decreasing in value. So that means we're going to have a negative common difference. So for this one, the common difference is 7 minus 13, which is negative 6. So just take the last value. The last value in our list was 1. Subtract 6, you get negative 5. Subtract 6 again, you get negative 11. Negative 11 minus 6 is negative 17. Negative 17 minus 6 is negative 23. All right, so now we graph those points. First point we want to graph is 1, 13. All right, so I'll leave the x-axis counting by ones, but then the y-axis counts by 5. All right, second point is 2, 7. Then 3, 1. 4, negative 5. 5, negative 11. 6, negative 17. And 7, negative 23. All right, In number 3, the common difference is the second number minus the first number. So common difference here is negative 31 plus 28 or negative 3. So even though it kind of looks like the numbers are going up, because they're negative, they're actually going down. So we decrease the next one by 3 again. We get negative 37, negative 40, negative 43, negative 46. So now we graph those points. First one is at 1, negative 28, 2, negative 31, 3, negative 34, 4, negative 37, 5, negative 40, 6, negative 43, and 7, negative 46. All right, so what I want you to notice is that when you graph the terms of an arithmetic sequence, it looks linear. So the terms of an arithmetic sequence follow a linear trend. For the next 3 problems, we're doing geometric sequences. So this is where you multiply by some constant to get the next item in the list. The way you could figure out this common ratio. So hopefully you could just look at it and tell what is being multiplied. But if you're having trouble, you take the second item and you divide by the first item. So 1/4 divided by 1 over 16. We know that if you want to divide by a fraction, you multiply by the reciprocal. So we end up with 16 divided by 4, which is 4. So the numbers are being multiplied by 4 to get the next term. All right, so if the last number was 1, we multiply by 4. We get 4. 4 times 4 is 16. 16 times 4 is 64. And 64 times 4 is 256. All right, now let's graph those items. So the first one is going to look kind of like it's at 0 because it's just barely above 0. Same with the second one, 2 comma 1/4. Right, then 3 comma 1. Then it starts to rise a little bit, 4 comma 4. The fifth number was 16. 5 comma 16. The sixth number is 64. 6 comma 64. And then the 7 comma 256 does not fit. All right, so before we move on, look at the trend that a geometric sequence has. It does not look linear. So we've learned about this before. It looks like it starts out flat and then it increases really quickly after that. That's called an exponential function. So a geometric sequence will look like an exponential function. And we compared that to Superman, the ride. So Superman, the roller coaster, starts out flat and then it goes up really quick. All right, for number 5, the R value is the second number divided by the first number. So 4 divided by 20 is 1/5. So we're multiplying by 1/5. If you take 20 and multiply by 1/5, you get 4. You multiply 4 by 1/5 and you get 4/5. And now we keep going. Times 1/5, you get 4/25. Times 1/5 again, 4/125. Then 4/625. And then 4/3125. first point is 1, comma 20, then 2, comma 4, and then 3 4/5. And so we learned about this as well before. This kind of looks like Superman the Ride, but from the other side. Then it just gets really close to 0. And it looks like I'm on 0, but we know that it's just going to become smaller and smaller, but 0 is actually the asymptote. For number 6, let's start by finding the R value. We take the second number, divide by the first number, you get positive 1/2. So we just keep multiplying by 1/2. The last number was -6. Half of that is -3. -3/2, -3/4, -3/8. All right, first point is 1, comma 24, 2, comma -12, 3, comma -6, 4, -3. Right, our R value was 1/2, and notice that the distance from the x-axis is being cut in half. All right, on the back of the notes, we're trying to figure out if the sequence that they show is arithmetic, geometric, or neither. So you can just check these in that order. So could it be arithmetic? Just kind of eyeball it. That went up by 9. That went up by 9. That went up by 9. So because it's always plus 9 each time, that makes it arithmetic. All right, they don't ask us to do this, but in the future, you will need to identify the common difference. All right, number 2. So if we check if it's arithmetic, this went up by 10, but that is not an increase of 10. So it's definitely not arithmetic. Now let's check if it's geometric. All right, so if I'm seeing if there's a consistent common ratio, when I go from there to there, that's 2 divided by -8, which is -1/4. All right, let's check this one. -0.5 divided by 2, that is also -1/4. And then there to there, 0.125 divided by -0.5, that also equals -1/4. So every time we divide a term by the term before it, we get -1/4. So this one is geometric. And I won't write the R value because it's pretty obviously -1/4. Right, for number 9, let's see, +2, +2, +2, but then the last one is not an increase of 2, it's an increase of 8. So this is not arithmetic. Now, could it be geometric? This multiplied by 3, but it did not multiply by 3 again. So this one is neither. It looked arithmetic at first, but you have to check it until the end of the list that they show you. All right, for number 10, so some people might not like these fractions. If I change these to decimals, it's a lot more obvious. So if I change 5/2 to 2.5, and then I change 7/2 to 3.5, you can see that it went up by 0.5, went up by 0.5 again, and went up by 0.5 again. So this is arithmetic because it's always adding 0.5 to the last term. All right, for number 11, We have a school. They started with 26 students. They enrolled 3 students each week. So that sounds like adding. We want to know when they will have 101 students. All right, so it sounds like they're adding 3 students each week, which means it's an arithmetic sequence. We saw when we were graphing earlier that an arithmetic sequence looks linear. It follows a linear trend. So we don't have to think of this as a series or as a sequence. We can think of it as a linear equation. So they have 26 students today. They're going to add 3 students each week. We don't know how many weeks, so I'll call it W. We want to know in how many weeks will it be 101. All right, so that's a basic 2-step equation. Subtract 26 from both sides. We get 75. So it will take 25 weeks. Assuming they can stay on that consistent trend. All right, and then in the last problem we have a pattern of rings. All right, so the way I'm looking at this is a ring. I'm not going to count the square in the middle as a ring. That's just a square, but if you look at the ring that I kind of traced, if you consider that white box in the center as the whole, then it's kind of a ring. And then this is also a ring. And then we have a bigger ring on the outside. So 3 rings. All right, so the first ring was kind of a 3 by 3. So each side was 3. How many squares were there? Well, if you count them, there's 8. And then you could also see that it's kind of like a 3 by 3 square, but with a hole in the middle. So 3 by 3, but then take out the one missing in the middle. So that first inside ring has 8 squares. All right, and then look at the medium ring. So if you count it, it's 5. It's like 5, and then 5, and then 3 and 3. So if you count it, there's 16. And then if you take the time to count the last one, there's 24 squares in that outside ring. So it's pretty easy to tell what the pattern is. It's 8, then 16, and then 24. It's just adding 8 each time. So it looks like you could be doubling it, but then when you go from 16 to 24, that is not times 2. So it's plus 8. You need at least 3 terms to tell what the pattern is. If you can only see 2 terms, there's no way to tell whether it's arithmetic or geometric. You need at least 3 terms to tell. You need to be able to tell if the pattern going from the first to the second number is the same as the pattern going from the second to the third number. All right. If the pattern is continued, write a formula for the number of squares in the nth ring. All right, so a few ways we can do that. I'm going to introduce you to the notation that you're going to see later in the chapter. So the notation you're going to see is, we're used to y equals. It's going to say a with a subscript of n. So a sub n equals. All right, so you guys are used to seeing y equals mx plus b. When I'm writing equations, I like to do something similar. So again, looking at the pattern, it's plus 8, plus 8. So the common difference is 8. I like to plug in the common difference right there. All right, so it's going to be, that's basically our slope. However, it doesn't go in front of x anymore. It goes in front of n. All right, and then as far as your plus b is concerned, I like to imagine I'm plugging in 1 for n. And if I plug in 1, I already get the first number that I want, so I don't really need a plus b. So I'll show you guys later in the chapter a few ways to do this, but I think this is a good quick way to write equations. So again, you kind of write y equals mx plus b, but instead of y, you write a sub n. M is not the slope anymore, it's the common difference. The x is changing to n, and then I kind of just figure out b by plugging in 1 and seeing if I'm at the number I want or if I need to add or subtract. All right, the last problem is asking not about how many squares are in each ring, but how many or how long the side is of the nth ring. So the first ring had a side length of 3. So if you look over here, this side length is 3. The second ring had a side length of 5, and then the next ring had a side length of 7. All right, so I hope you can see the pattern. So it went 3, then 5, then 7. All right, I'll start with a wrong answer. Is that geometric? Well, this multiplied by 5/3, but it did not multiply by 5/3 again. So it's more obviously arithmetic because increase by 2, plus 2, and then plus 2 again. All right, so we want to be able to say that as a function of n. All right, so again, I'm going to use this notation because you're going to have to use it a lot this chapter. So again, what I like to do is kind of do y equals mx plus b. I figure out what the common difference is. That is my m. And then that multiplies in front of n. All right, and so I was saying what I like to do is plug in 1 for n right there and see if I get the first number I want. And I don't, so I know I need to increase by 1. All right, so we'll do this more in depth later in the chapter, but that's one of a few ways to write an equation for the nth term of an arithmetic sequence. And they didn't ask for an equation, I guess, so they just asked how long is the side in the nth ring, so I guess only that part is the answer. All right, that's it for 10.1.